Hello guys, so it's time now to discuss another important application, maybe the most important application for transistors, which is basically amplification, amplifiers. How to design, or how to use a transistor in a circuit to amplify some small signal into a big signal. Okay, so usually these circuits amplify AC signals. So now we're gonna assume that our input, the input for the same circuit that we just analyzed it for to get the transfer characteristic has a little bit of variation. So we're gonna assume that this input has a DC voltage of 1. I'm gonna explain why we need this DC voltage, plus some small in a signal. Basically, the real input that we wanna amplify is basically this one, the AC portion of this input. If we want to draw or plot this input, this is basically a DC or AC superimposed on a DC. So this is, for example, the input with time here. This is 1 volt. Then you have very small AC sine signal like this. And the maximum is 105 because basically the sine itself, sine theta maximum is 1. So 1 times 0.05 will give you 0.5 plus 1, it will give you 105. And the minimum is 0.95 because the minimum of sine theta is -1. -1 times 0.05 is minus 0.05 plus 1 will give you 0.95. Okay, good. So that's basically the input. Now I'm gonna, forget about amplification. I'm gonna just consider 3 points. The point at which the AC variation is 0. I mean sine theta is 0. And the point at which sine theta is 1, and the point at which sine theta is -1. Okay, because basically this will determine, or give us a highlight about what would be the output here. Okay, so let's analyze the first one. Remember, the relation between VO and V input in active region is basically this, this equation here, 17 minus 10 V input. Okay, so let's check when sine theta equal to 0, what's gonna happen to V output. So basically V input is when sine theta is equal to 0 will be just 1. Okay, just 1. So let's check V output at that time. So V output, oh yeah, before this, let's check first on the, on the axis here. When V input is 1, where is exactly V output? Is it active? Is it saturation? Is it cutoff? Let's check. So basically, cutoff region ends here when V input is 0.7. Saturation region starts here when V input is equal to 1.65, 1.68. So V input now is 1. Where is 1? 1 is basically in between these 2 points here, for example. So at V input equal to 1, we are in active region. Okay. So we are in active region. So we can use this equation. That's why I say stop. No, we should first check where is V input, where is V output basically when V input is 1. So we can use this equation, safely. So the output at that case is equal to 17 minus 10 equal to 7 volt. So this is basically here 7 volt. Good. Now let's put sine theta equal to 1. So basically the input will be 1.05. So we can do the same. 1.05 on the axis here is basically just, beside the 1. It's still less than 1.6 and higher than 0.7, of course. So still an active region. So we can use this, this equation again because we're still in active region. So 17 minus 10 times 105. This is basically 17 minus 10.05, 10.5, I'm sorry. So this is basically 6.5. 6.5. So let's assume this is, for example, this point, this small point here is basically the 1.05. So if we go up, This would be 6.5. Good. Number 3, when sine theta equal to 1 minus 1 this time. Basically the minimum of the input. When sine theta is 1, this is maximum input. When sine theta is minus 1, this is minimum, the minimum input. So the input here is 0.95. So VO again 17. Again 0.95 is basically just after the 1. Let's say it's in here. It's bigger than or greater than 0.7 and less than 1.68. So we're still in active region, so we can still use the equation. So V out is equal to 17 minus 10 times 0.95. So it is basically 17 minus 10.5. It's basically 7.5. So V out is equal to 7.5 when V input is equal to 0.95. So let's say it's in here. That point 7.5. Before I continue, before any continuation, okay, let's check what is the voltage peak to peak of the input and the voltage peak to peak of the output without even knowing what is the output. Okay, so we discover the following. First, the input peak to peak is basically between 1.05 and 0.95. So basically the voltage peak to peak here is 0.05 plus 0.05, it's 0.1 peak to peak. Look at the output now. So the output will change from 6.5 to 7.5. What is the voltage peak to peak here? It is basically this distance. So the output peak to peak is basically 1 volt. 10 times 0.1, right? So we amplified basically the input by 10 times. And we can draw that, by the way. So let's do now the full plot for the input and the output. So we can, we're gonna draw it in a very weird way, but it's correct. Don't worry about that. So we're gonna draw the sign like this, the input. So basically the output will be, so this is, remember, this is the one. This is the corresponding output when the input is equal to 1. This is our 0 now. We can consider it like this. And this is the output when the input is 1.05. And this is the output when the input is basically minimum 0.95. So this is gonna give us something like this. Now compare the input here by the output here. So the output basically would be 7 plus half sine omega t. This is what's exactly happened. Okay. So if we ignore the DC portion of both input VO and V input, which is 1 here and 7 here, look, the AC portion was here 0.05 sine omega t, and here it's 0.5 sine omega t. So it's multiplied 10 times, right? So there is amplification here by 10 times. And this happens in the active region. But how we could do that in the first place? We could do that by having a DC portion in the input that makes us between 0.7 and 1.65 in this region, in between here. That's why it's a DC, and there is a superimposed signal, which is the AC signal, which is basically the original signal that we want to amplify. But we can't feed the 0.05 by itself to the circuit, because without this 1 volt, here. Why? If we do that, we will be here in the cutoff region. That's why we have this DC. Although we want only to amplify this 0.05 sine omega t. Okay? Again, we put the DC here to be sure that we are working in the active region. Now another question. What is the best operating point? So operating point mean which is basically the biasing point. If we don't have AC, in the input, I mean, let's assume that 0.05 sine omega t is not there. Basically, the input at the time will be just equal to 1, right? So what is the corresponding out? The corresponding out will be 7. So 1 and 7, the input is 1, the output is 7 is basically our operating point. We can say it's our reference. The reference for the input is 1, the reference for the output is 7. Okay? But what is the best point? What is the best input, DC input, and what's the best DC output, we can say. So I'm gonna answer this using the counterintuitive in a counterintuitive way. Okay, so let's say that, let's change the color, that we choose, basically we want to operate in the active region. Okay, to have this amplification. This is basically the amplification. This is the 10 times come from here, from the slope. Okay, that's why we want to operate in the active region. So we're gonna take the slope 10, and this is basically what happened. We amplified the 0.05 to 0.5. Now, to answer where is the best operating point, we're gonna make the operating point on the edge of the cutoff and the edge of the saturation, and we're gonna see what's gonna happen if we do that. Okay, so let's start, for example, by the edge of the cutoff. Same input, but now it is 0.7 plus 0.05 sine omega t. Okay, we're gonna do the same. What's happening at the input equal just to 2.7 when the sine omega t is 0, basically. So basically the output will be equal to VCC. How we could know that? This is really easy. At 0.7 here we have VCC, which is 10 volt. Good. Number 2, when V input maximum equal to 0.75, yes. When sine omega t is equal to 1, this will be 0.7 plus 0.05, it's 0.75. So at that time, we are higher than 0.7. At the same time, we are less than 1.68, the input set. So we're still in the active region. We can use this equation. So the output will be 17 minus 10.75. So 17 minus 7.5. This is basically 9.5. No, yes, 9.5. Yes, 9.5. Okay. Number 3. And most importantly now, when the input equal to, at sine omega t equal to -1, this is basically will be 0.65. Oh, 0.65 is basically here, less than 0.7. So the transistor will be in cutoff. So the output for sure will be equal to VCC equal to 10. It's not like here. We are using this equation all the time. So this 10, this multiplication factor, what we can call gain, this amplification gain is applied all the time. But now no. And basically, if we draw the output in that case, the blue case here, it will be something like this. Then 0. Then go down again, then 0, then go down again, then 0. So basically, you get half of the signal amplified and you lose completely the other half. The positive half will just go away. Only the half of the portion of the signal, which is basically half of it here in the active region, only the portion in the active region will be amplified. The half that was in the this half, this half here, which was in the cutoff, will just go away, will just be 0. Clipped. This is called negative clipping. I'm sorry, positive clipping. So this is called, and this is called cutoff distortion or cutoff clipping distortion. Look, we have clipping everywhere in diodes, in transistors. And this is, of course, distortion. It is distortion for the input signal. The input signal was a sine wave like this, and look what we get, half of a sine wave. Yes, it's amplified, but where is the other half? Good. So it's not good to make the operating point near the cutoff region. Is it good to make it near the saturation region? Let's check again. Let's have another color. Let's do with this guy, for example. So we're gonna put a sine wave. This time it is 1.68, which is the input set, plus 0.05 sine omega t or sine theta. Number one, when sine omega t is equal to 1, the input will be 1.68. It's in here. At that time, VO is equal to 0.2. Number two, when the input equal to, when sine omega t or sine theta is equal to 1, the input will be 168 plus 0.5. This is basically 1.73. What is the output in that case? So this point is basically higher than 1.68. So the output will be 0.2. Again. Number three, the input when sine omega t equal, when sine omega t is equal to -1, the input will be 168 minus 0.05. This is basically 1.62. This is less than 1.68, so it will be amplified. And we can determine the output at that case. We can use this equation. So it will be 17 minus 10 multiplied by 162. So 17 minus 16.2. This is basically 0.8. The output will be 0.8. Okay. So what's happening here? Here we have another sort of distortion. So for all the values, these values that I'm highlighting here, that is the input is greater than 1.68, greater than the input set, it will be clipped as well. And only this portion which is in the active region will be amplified. So we're gonna see something like this time. 0 or whatever, 0.2 here in that case. This is another way of distortion. This is now saturation cutoff distortion. And again, it's not good. You could amplify, but you could amplify only half of the input signal. Half cycle of it, basically. Not all the cycle. So we can't put, the operating point near the saturation region as well. So basically, the best way or the best point or best operating point to use the transistor as an amplifier is to put it in the middle of the active region. So let's write this down. So the best operating point for the transistor to work as an amplifier is in the middle of the active region. So you're gonna have what's called maximum swing to get maximum swing in the output. The middle here means middle between the 0.7 and the input set. The input set. Okay. So at that case, the input will be equal to 0.7 plus V input set over 2. Or you can say middle is mean, which is basically equivalent, very equivalent, and even better. I'm gonna say why now. Middle between, for the output now. No, here is for the input, now this is for the output. Between VCC and 0.2. Because when V input is equal to 0.7, V output is VCC. When V input is equal to V input set, V output is 0.2. So you can refer to it using the input or the output. So when VO equal to VCC plus 0.2 over 2. The average, you know, when we calculate the average between 2 points, we add them together, then divide by 2. For example, 2 and 4, the average is 3, right? You can't say 4 minus 2 over 2. This will give you 1. But to get the average, which is 3, you should add 4 to 2, which is 6, then divide by 2, this will give you 3. Okay, that's what I have done here. VCC plus 0.2 over 2. Or you can just ignore 0.2. Usually VCC is, you know, 5 or 10, 12, 15. So usually 0.2 is really negligible to it. So this will be equal to VCC over 2, ignoring the 0.2. So you can set your VCE, usually the output is equal to VCE, to VCC over 2, or you can control the input to make it between some point between 0.7 and V input sets, okay, to get the maximum swing. Okay, guys, that was basically, a very good introduction about how to use a transistor as an amplifier. In the next recordings and videos and lectures, we're gonna delve into deeply, basically, into transistor amplifier circuits, how to analyze it, how to get amplification, how to draw what's called equivalent circuit, ECC, small signal equivalent circuit, which will make your life very easy dealing with transistor amplifiers. So thank you very much for watching this video, and see you in the next video. Bye-bye.